Okay, students, so let us start. You're able to see my screen, right? Hello, students?
Yes, sir, it is visible.
Hello, students?
Yes, sir.
You're able to listen to me. The voice is not audible. Okay, so I don't know. Your voice, I'm not able to hear. So your voice is not coming to me anyway. If you are able to listen to me, you can just follow. All right? So I'm continuing. So I told you that we are going to see this like NMR spectra. Uh, so as I told you, all this like electromagnetic radiation that can be used for uh, studying the molecular properties. The molecular properties you can do, and also you can use them to analyze the structures as well. Okay. So recently we finished with X-ray spectroscopy, right? Otherwise we call it like X-ray crystallography. So for studying the small molecule as well as the macromolecule, you can use the X-rays, right? So similarly, we can use the nuclear magnetic resonance (NMR). Okay, NMR to study the uh, properties of the molecules. Okay, so NMR, it is used in like various field, right? Even in medical field, that NMR is used. Okay, so here we are going to see like how the NMR is helpful to study the molecular properties. Okay, so you can use the NMR to find out to solve the structures of the macromolecules as well. Okay, so why you want to solve the structures by using NMR? Already like X-ray crystallography is available, X-rays are available, right? So why you want to study the NMR? So in the beginning, I have told you like you can do the you can solve the structures of the macromolecule by using the X-rays. Okay. Suppose if you are not able to get the crystal, what will you do? With the crystallography, I told you that several problems are there. Okay, so you have to clone the protein, you have to purify the protein. If purification is giving you like problem, okay, so you have to truncate the protein. Either you can try like N-terminal or like C-terminal alone to purify, or to clone only like certain area, like that. Okay, so then expression problem, then purity. So all these things, right? You have to come across, and then you have to screen like thousands of conditions. Like for say like crystallization, you have like so many factors. So all those factors that you have to come across, and finally whether it will diffract or not, that you do not know. Right? So it's a crystallography. It's like a tedious step. So you are going through like one by one, right? And finally, whether it is giving structure or not, again that is a problem. So like X-ray crystallography is like a very like a tedious problem. Okay, but if you are able to come over all this problem, you will get the structures at atomic resolution level. Okay, In case you have tried like all these things, still you are not able to get like a crystal structure. So in that case, what you will do? So you can do the NMR spectroscopy. Okay, or else you have solved the protein structure by using X-ray crystallography, but you want to find out the solution behavior, how the protein is behaving in a solution. Okay, so that you can do in the NMR spectroscopy. Okay, so NMR spectroscopy comes second importance in the experimentally solving the crystal structure. Okay, experimentally solving the structure of the macromolecules. Okay, so there is a basic difference between like the structures that you are getting from like X-ray crystallography and from NMR spectra. Okay, what's the basic difference here? So the basic difference is like in X-ray crystallography, you are trying to take an image of object which is in a resting position, right? You are crystallizing the protein or like nucleic acid, whatever, the macromolecules you are doing crystallization. In the crystal, your protein is in nearly zero movement. Okay, listen carefully, it is nearly, okay, it is not completely like zero movement. It's nearly zero movement, and you are taking an image of like an object which is not moving. Okay, whereas in NMR spectroscopy, you are not using protein crystals. You will be using the protein in solution. Okay, in solution, what will happen? You know the Brownian motion, right? Any particles in a solution, it will be in a random movement. So it will be in a continuous movement here and there. So each particle will be like colliding with each other, and the acceleration, right? It will increase or decrease, whatever. All this movement will be there. It's a random movement. Okay. So protein molecule in solution is going to be having like the same kind of motion. Okay. So the protein will be in a continuous motion. So the loop region, whatever. Okay. So you have like a loop region here in this like protein. So they will be like in a continuous motion. The secondary structure, it will be going like to and fro, right? So the protein will be like in a continuous motion. So you want to take an image of an object which is in a continuous motion. Okay. Whereas in X-ray crystallography, you are taking a picture of an object which is not moving. Whereas in NMR, you are trying to make a photograph of like a moving object. Right? So what will happen ultimately? So in X-ray, since the object is not moving, you will get an image just like this, right? But in NMR, the image will be blurred. Yes or no? Say yes or no, yeah? I don't know. And your voice is not audible to me. Students?
Yes, sir.
Yes, sir.
Okay. Yeah. Now I can listen your voice. Okay. So what will happen? So you are trying to take a photograph of like a moving object. What will happen? The image will be blurred, right? So in that case, if you want to take the picture, what you have to do, you have to take like images of like several times. So when the object is like moving, you have to take like several photographs, and you try to overlap all these like blurred images, right? And then you will try to get an like a average image of that. That's what you can do, right? When you're trying to take a photograph of like a moving object, you have to take like a several snapshots and then average it so that you will get an image. So that is exactly happening in NMR spectroscopy. Here in crystal, you have like a object in a resting position, whereas in solution, you have like a movement. The molecule will be in a continuous movement, continuous motion. Okay, so that's why if you go to the PDB, okay, so go to PDB and take a protein structure which is solved by X-ray crystallography as well as the NMR. Okay, so here I have given like this proteorhodopsin. Okay, so the structure is available in the X-ray method as well as in NMR method. In X-ray method, you will see a set of coordinates. Okay, only one time. Okay, so is anybody have seen the PDB file? Guys, have you ever visited PDB site? And
Yes, sir.
did you download the protein structure?
Yes, sir.
Yes, sir.
So what did you see in the PDB file?
The coordination of atoms.
Yes. So you will see the coordinates for each and every amino acid, right? So in amino acid, you will have like 5 or 6 atoms. So each atom will be having like a X, Y, Z coordinates, right? So these coordinates only you will see in like PDB file for continuous protein. Suppose you have like a protein of like a 500 amino acid means like all the like atoms in the 500 amino acid will be listed continuously, and you will see the coordinates X, Y, Z, right? So this coordinate will appear only once for the structure that is solved by X-ray. Whereas if you see the NMR structure, the same protein, you will have the coordinates for like 5 or 6 times or like even 10 times. Okay, so what is that? That is ensembled. Okay, ensembled. So as I told you, you are trying to take a moving object, you will take like a several snapshot and an average structure. What you are getting in a NMR spectroscopy is an average structure. Okay, so that's why here in ensemble you will see the movement of the loop region, movement of the secondary structure elements. Okay, whereas in X-ray everything will be in a fixed position. You will see the loop only in this conformation. Okay, but whereas here you see the loop region. Okay, so one time it is in this orientation, another time it is like moved somewhere, and another time it is moving somewhere. So here and there you can see the flexibility that you can see in NMR spectroscopy. So what is the advantage? So you can easily find out the conformational change. Okay, so when you are studying kinetics, right? So you have like some enzyme, something like this. So you have the active site here, and you are trying to find out the substrate binding. Okay, so your substrate is there, and this is the active site, right? So in the native form, okay, assume like you have some conformation, something like that. Okay, So you have the active site here, and you want to find out the how the conformation is changing here. So when the substrate is binding, okay, so you can see this region, this conformational change. Okay, so this you can easily find out in like NMR, because you are able to capture the images of all these things. Whereas in a crystallography, okay, either this image or this image, only these two images that you can study. The intermediate, okay, that you cannot study in NMR. So that's the basic difference between like NMR and like X-ray crystallography. Okay, so next hour Suresh sir is taking for you, right?
Yes, sir.
So don't worry, I am going to take. I have told him, because we have this like power problem, so it took long time, and so that's why I told him that he also told me to utilize the class. Okay, so don't worry. So I'm continuing the class. So same thing like for protein or like a nucleic acid, that you can use the NMR to find out the structures. Okay, so here just we are going to see from the basic. All right. So whatever that I have discussed so far is like for like giving you like overall idea about like NMR spectroscopy, and to know about the basic difference between NMR and X-ray crystallography. So now we are going to see the basics of the NMR spectroscopy. Here you can see like you have like a high energy radio waves, and you have like a low energy, right? So you know the electromagnetic radiation, EMR, right? Electromagnetic radiation. So you know the wavelength of all these electromagnetic radiation, different wavelength, and depending upon this like wavelength, you have the energy variation also. You have like high energy photon, you have like a low energy photons as well. Okay, so you have like high energy photons, and the wavelength is like very small. Okay, so you have like a very smaller wavelength, and you have a higher energy, and you can see like high energy photons, which is having like a very lower wavelength. Okay, so for example, like X-rays and gamma rays, right? So these, okay, the high energy particle, okay, high energy, this wavelength, you can utilize for studying the structures of the molecule. All right, and you can see this like visible and UV light. Okay, so here you can study the molecule, the electronic properties of the molecule. Okay, and you can see this like IR spectra. So IR spectra, again, you can utilize the IR spectra to find out the molecular vibration. Okay, and then you can still, the wavelength is still lesser. You can study the rotational movement of the molecules, and then you have like a radio waves, which is having like a very longer wavelength. Okay, the wavelength is like very long, and still you can use those for doing the structures of the molecule. Okay, so you know the frequency of the like wavelength, and you know the energy of the electromagnetic radiation as well. Okay. So NMR is the like most powerful tool available for finding the organic structure of the molecules. Okay, so it is used to study like wide variety of like a nuclei. So and you know like a proton, C13, N15, F19, P31. Okay, so all these nuclei that you can to study these. Okay, you can use the NMR. Okay, the nucleus with an odd atomic number. Okay, whatever I have shown you, right, is an example for an odd atomic number. A nucleus with an odd atomic number and or an odd Morse number has a nuclear spin. Okay, so the nuclear spin that here in NMR, the important thing that you have to note down is like nuclear spin. Okay, so the spinning charged nucleus generates a magnetic field. Okay, so here the nucleus, which is having like an odd atomic number or like odd mass number, will be having like a spinning, which will be having like a magnetic field. So here you see a bar magnet. Around a bar magnet, you know that there is a like a magnetic field, right? Around a bar magnet, a loop of current is like flowing. Okay, the same effect that you can find out in a spinning nucleus, okay, which is having like an odd atomic number or odd mass number. So, and when you are keeping an like a nucleus with odd atomic number in an external magnetic field, okay, so it will be behaving just like a bar magnet. So you have like a spinning nucleus and you have like an external magnetic field. The magnetic field strength is B naught. Okay, so it will twist the nucleus. The spin of the nuclei will be like twisted. Okay, so here you see like this is like a low energy, which is like a more stable, whereas like south and south it will like a repel each other, right? Which will be like a high in energy and less stable, right? So the same thing, if you use the like a bar magnet, right, in an external field, so it will be like a spinning. The bar magnet will be like a spinning, just like a bar magnet, right? So there are like two energy states. So the magnetic field of the spinning nuclei will align either with the external field or it will be against the magnetic field. Okay, a photon with the right amount of energy can be absorbed and cause the spinning proton to flip. Okay, so only like a two case. Okay, so this is like external magnetic field strength B naught. So either the nuclei will align with this or it will be opposing the external field. Okay, so there are like two different energy states. So this is external magnetic field. So it will be either aligning with the external field or it will be against the external field. So if it is aligning with a B naught, the energy is very low. It is called like an alpha state. If it is opposing, the energy is very high and it is called like a beta state. Okay, so the H nu is equal to del E. All right, Suraj, you are able to follow, right?
Yes, sir. Yes, sir.
Yes, sir.
Okay. So here, so suppose you have like a proton. Okay. So you have a proton in alpha state, that is in a low energy state. If you want to flip this like nucleus, if you want to flip this, so what you can do? You can apply some energy and you can make this to flip the direction of the spinning. Okay, so for that you need to apply some energy. Okay, so that's what here. Okay, so and right amount of energy can be given to make the spinning of the proton to flip. All right. Okay, so only these things will cause the NMR spectra. Okay, so the NMR signal, okay, depends on the applied magnetic field that causes an energy difference between like aligned and unaligned nuclei. So NMR signal results from the transition of spins from alpha to beta state. Okay, so if you are able to flipping, okay, that will result in an NMR signal. The signal strength, okay, depends on the population difference between the alpha and beta state. So how much population you have, right? How much crowd you have here. Okay, so B naught is greater than 0. Okay, so the population difference can be determined from the Boltzmann distribution and the energy separation between like alpha and beta spin states. So NMR signal depends on gyromagnetic signal depends on this like formula. So S is equal to gamma power 4 B naught square N beta 1 N B1 G of mu divided by T. Okay. So number of nuclei N, gyromagnetic ratio gamma, and then temperature and so on. Okay. So in general, okay, don't worry about the explanation of all these things. Just remember this formula. Okay. So you have to increase the energy gap. So you have the energy gap here. You have to increase this energy gap. Okay. And then increase the population difference. That will result in a good NMR signal. Okay. So del E should be higher. The B naught should be higher. Gyromagnetic ratio should be higher in order to get a good NMR signal. Okay. So increasing magnetic strength is a major means to increase the sensitivity. Okay. So you can see the like how much you have to spend as well. Okay. So this is like a 900 megahertz, this is like 800 megahertz, I guess this is like a 600 megahertz. Okay. So as a result, you have to spend like too much money as well. Okay. So relative sensitivity of like a proton, C13, N15 and other nuclei depends on like two factors. One is like gyromagnetic ratio and another is like a natural abundance. Okay, how far it is available. So here you can see like a gamma intrinsic property of nucleus cannot be changed. Okay, so gyromagnetic ratio for C13 is 64 times. Okay, whereas for like N15 it is like 1,000 times. Other words, I can say like proton is like a 64 times as sensitive as C13. And C13 is like 1,000 times sensitive, and again, proton is 1,000 times sensitive for like N15. Okay, so consider the natural abundance of like C13 is like only 1.1%, and N15 is like 0.37 percentage. Okay, whereas like proton is like a huge. Okay, so here you can see like a proton nanomole spectra of caffeine. It's a molecule caffeine. Okay. So just expose like 12 seconds for 8 scan, you are getting like a very nice peak here, right? The same thing like with using like C13 isotope, right? The same molecule caffeine, only the same like time scale. Okay, just 12 seconds and the 8 scan, you are getting a peak like this, with a large amount of signal to noise ratio, right? You have like a lot of noise, right? If you want to get like a peak just like this, so you have to do how much? 4.2 hours, right? And then you have to do like 10,000 scans, right? So these and these are somewhat like this, looking like closer, but what's the time? How much cost it is, right? So that is the sensitivity. Okay, it is because of the relative abundance of like these isotopes. Okay, so in proton you have like plenty of the thing readily available. All right. So del E and magnetic strength. So energy difference is like a proportional to the magnetic field strength. So del E is equal to H nu, which is equal to gamma H divided by 2 pi V naught. So gyromagnetic ratio, gamma is a constant for like each nucleus. Okay, so it is like 26,753 per second per Gauss for proton. Okay, so in a 14,092 Gauss field, a 60 megahertz photon is required to flip a proton. Okay, so low energy radio frequency if all protons absorb the same amount of energy in a given magnetic field, not much information could be obtained. Okay, what does it mean? If all protons, assume you have a methane, right? CH4, right? CH4. If all protons absorb the same amount of energy in a given magnetic field, not much information could be obtained. Okay, but protons are surrounded by electrons that shield from the external field. Okay, circulating electrons create an induced magnetic field that opposes the external magnetic field. Okay. So magnetic field strength must be increased for a shielded proton to flip at the same frequency. Okay, you have to increase the magnetic field strength for a shielded proton. What is shielded proton? We'll see that. I will explain you in a little while. So here you can see, assume this is a proton which is not surrounded by any electron. So there is no shielding effect. So the proton, this nucleus is free to expose to the external field. Okay. So we know that 14,092 Gauss B naught, external magnetic field. So 60 megahertz frequency is enough to flip the proton. Okay. So naked proton observed at 14,092. Okay, 14,092. Okay. Assume you have a proton which is surrounded by the electron. The sphere you imagine as an electron. So you are applying same 60 megahertz frequency. Okay. You have the external magnetic field strength. Okay. But the proton will not absorb. It will not cause the flip of the proton. It is because the electron is shielding. Okay. So in this case, you have to apply little bit higher magnetic field. Okay. So here 14,092. So increase slightly 14,092.3 Gauss, which is stronger than here. Okay. So that will cause the proton to absorb, and hence the proton will flip, so that you will get an NMR signal. Okay. So this is the difference. So you have the proton, okay, which is surrounded by electron. So if you apply, okay, electromagnetic radiation, okay, so since you have a proton here, so it will be shielding. Okay. So if you increase the magnetic field strength, so that will make the NMR signal. Okay. So the difference between a naked proton and a shielded, okay, shielded proton, you should know. All right. Students, you are able to follow. You are understand. Do you understand? Guys, do you follow me?
Yes, sir.
Sir.
Yes, sir.
Okay. So as I told you, in a methane CH4, you have a 4 hydrogen. Okay. So not think about some other molecule. Okay. So each proton is having different chemical environment. Okay. So depending upon the chemical environment, so the protons in the molecule are shielded by different amount. Okay. Suppose in case of methane, I am replacing one of the hydrogen with chlorine. So the formula now CH3Cl. So what is the name of this? CH3Cl. Come on, yeah.
Chloromethane.
what?
So chloromethane.
Chloromethane. So I have like CH3Cl here. This is methane. So who said this chloromethane?
Sadia.
Sadia. Okay, no problem. So any other name for this?
Sir, methyl chloride.
Yeah, methyl chloride. Okay, this is another name. So Sadia also correct. Okay. So generally, people used to say this methyl chloride. Okay. So I am replacing again one of the hydrogen. Right. So what we now CH2. Okay, and Cl2. Okay, what is this? What is the name of this? It's a dichloromethane. Right? So and so on. So whatever. So don't worry about the names. We are not. I just wanted to test you. Okay. So what I want to say is, like in methane, you have like a only hydrogen. In methyl chloride, you have chlorine. Okay, dichloromethane, you have like a two chlorines. Okay, then CHCl3, chloroform. Right? You have like a three chlorine. Carbon tetrachloride, you have like a four chlorine. Okay, so you have like different chemical environments. Okay, so as a result, the protons will be like a shielded, in a different amount. Okay, so here you can see this is what CH3OH. What is this name?
Methanol.
Okay, so here you can see like methanol. Okay, you have like a four protons, but each proton is having like a different chemical environment. Okay, so here you can see this CH3. Okay, they are more shielded, whereas here the OH, it is less shielded. So the difference you should know. Why it is more shielded? Why it is less shielded? What is the effect that you should understand? Okay, so more shielded. Okay, the more shielded proton will absorb a higher magnetic field. Less shielded protons will absorb a lower magnetic field. Alright, so this difference you should know. Less shielded will absorb a lower magnetic field. More shielded absorb a higher magnetic field. Okay, so why it is like a less shielded? It is because the electronegativity of the atom to which the proton is attached. Okay, here carbon and oxygen is more electronegative, right? As a result, it will be like a slightly polar. Okay, it will try to pull the electron of the hydrogen towards the oxygen. Okay, so as a result, what will happen? The proton, you have the electron here, it will be pulled towards oxygen. As a result, the shielding effect of the electron for proton will be very less. Yes or no? So this proton will absorb at the lower magnetic field strength. Whereas here, the carbon is not electronegative. Okay, so each hydrogen is having its own electron. Okay, so as a result, the external magnetic field will be shielded. Okay, so they will be more shielded compared to this OH group, and they will be absorbing at a higher magnetic field. Okay, is it clear, students?
Yes, sir.
Sir.
Okay. So the NMR signal depends upon like four conditions. Okay. So the number of signals shows like how many different kinds of protons are present. Okay. So I told you, like you have like a methane, methyl chloride, dichloromethane, chloroform. Okay. So here, so each of these molecules will not give you the same kind of peak. Methane will give you some pattern of the peak. Methyl chloride will give you some pattern of peak. Okay. And CCl3, CH2Cl2, whatever. Okay. So the number of signals shows how many different kinds of protons are present. Okay. Based upon the signal, you can tell what kind of proton is there, that you can tell. And the location of the signal shows how shielded or de-shielded. Okay. Based on the location of the signal also, you can tell whether the proton is shielded or de-shielded. Okay. And then intensity of the signal will tell you the number of protons. Okay. So intensity, NMR signal intensity, you can find out the number of protons. Okay. And then signal splitting. In some cases, you will get like a single peak. Alright. In some cases, the same peak will be split into two. Something like that. Okay. So that's called like a signal splitting. It will show the number of protons on adjacent atoms. So assume like you have like a CH3 here. Okay. Here you have like a CH2. Sorry, it's not. Okay. So you have like a CH2 here, you have CH3 here. So for this proton, you will get like some signals. Okay. Here also you will get some signals. Okay. So here the signal splitting, it will tell you how many protons are here, how many protons here. Okay. So based on like NMR signal itself, that you can tell all these like property. Okay. So this is like a schematic diagram of like NMR spectroscopy. Okay. So you have like a complete like a magnet. Okay. And you have like a sample holder, and you have like magnet controller. Okay. So the sample is like hooked with like detector, and so you can like whenever you have like a signal, it will be recorded on a screen. Okay. So here we see the NMR graph now. So here you can see this is the increasing magnetic field strength. Okay, it is like a B0, I told you. So it's like increasing magnetic field strength. Okay. So you can see the less shielded. It is on your left hand side. On the left hand side of your NMR graph. Okay. So more shielded proton that always will appear on your right hand side of the NMR map. Okay. So less shielded proton will appear on downfield. More shielded proton will appear on like a higher field or upfield. Okay. So here you can see like these protons, they are like more shielded. I told you, right? Like previous slide. So here in the methanol, the same molecule, I told you these protons are like more shielded because they have like electrons revolving around the it. Okay, because it is attached to carbon, there is no electronegativity, so the electron will be surrounding the hydrogen. Whereas in oxygen, the electron of hydrogen will be pulled towards oxygen. As a result, it will show no shielding effect. Okay, it is less shielded. This proton is less shielded. So less shielded appear lower field. So here the less shielded like proton appear like downfield or lower field. Okay, so remember this NMR map. So left hand side on your map is downfield, right hand upper field, higher field or upfield. Okay. So these protons are highly shielded or like more shielded, so they will appear on upfield. So now, so you can see here, this is tetramethylsilane, TMS. So generally it's called like a TMS. Okay. So TMS is added to the sample. So whenever you want to take NMR, you will add like TMS to the solution. It's because silicon is here, the silicon is less electronegative. Okay, compared to carbon, the silicon is less electronegative than carbon. So TMS protons are highly sealed. Okay, so here these protons are highly sealed. It is because this silicon is less electronegative. Okay, so the signal defined as, so organic protons absorb downfield to the TMS signal. Downfield means what? Downfield means what, man? That's what I told you. Downfield means left hand side of your NMR map. Alright? Upfield means right hand side of your NMR map. So here, what is this saying? Organic protons will absorb downfield of the NMR TMS signal. Downfield of the TMS signal means what? So you will have like a TMS signal which is assumed like a 0. Okay, so here the scale will be like a 0. Downfield means left hand side of this TMS. Is it clear?
Yes, sir.
Okay. So the TMS, otherwise you can say it's like a standard, or in the scale, in the NMR scale, the TMS signal will appear at 0. Okay, all other like organic protons will appear downfield to this, because TMS is having no electronegativity. As a result, NMR signal will appear always at 0. Okay, so NMR signal, it is generally denoted in terms of chemical shift. Okay, it is measured in like a ppm, parts per million. So the chemical shift is a ratio of shift downfield from TMS to the total spectrometer frequency. Okay, it is a ratio of shift download from TMS to the total spectrometer frequency. So we can use the spectrometer frequency of like 60 megahertz, 100 megahertz, 300 megahertz. Okay, so assume like you have like a NMR signal. So this is TMR 0. So something like 1, 2, 3, 4, 5, something. Okay, so the ratio, assume like some molecule is absorbing at like a 5. Okay, so downfield towards TMS. Okay, so 5, the ratio. Okay, the ratio 5 divided by, if you are using like a machine of like 60 megahertz, 5 divided by 60, so that is the delta, which is called like a chemical shift. Okay, is it clear? Assume like you have a molecule, okay, which is observing at 5, okay, downfield from TMS, okay, the ratio of shift downfield, okay, downfield, this is the downfield, right? Downfield is what? Left hand side of your NMR map. Upfield is right hand side of your this NMR map, right? So downfield, so I have like a 5 divided by the spectrophotometer frequency. Okay, I am using like a 60 megahertz frequency. So 5 divided by 60. So that is called like a delta or chemical shift of that molecule. Okay, if I use like 100 megahertz, then 5 divided by 100 megahertz, that is the delta. Alright. So called in the delta scale. So here you can see chemical shift, which is given by ppm. Okay. So shift downfield from TMS inverse spectrometer frequency divided by spectrometer frequency. So I told you this is like a 0 TMS. Okay. From TMS downfield. Okay, whether it is like 1, 2, 3, 4, whatever. Okay. So wherever, like you suppose you are having like a 10 means 10 divided by 60. See, this is like a 60 megahertz. Okay. So this is 300 megahertz scale frequency. Students, do you understand or not?
Yes, sir.
Okay. So now we'll see some example for location of signal. Okay. So as I told you already, so assume this is like a methane. You have the molecule CH4. Okay. So you can see the chemical shift delta is 0.2 for methane. I am replacing one of the hydrogen with chlorine. So methyl chloride. Now the delta is 3.0. What does it mean? Come on here. So here for methane, the chemical shift delta is 0.2. Okay, you draw the scale. You draw the scale, you have the TMS 0. So from here 1, 2, 3, so forth, right? 1, 2, 3, and so on. So for methane, you have 0.2. Whereas methyl chloride, the delta value is 3.0. What is the meaning of this? If you understood, and if you understood whatever that I have told you this so far, you should be able to tell you right now. I have drawn the scale also. Everything is there.
Sir, I think it is very far from the TMS.
Now tell me the meaning. So assume like you have like a scale like 1, 2, 3, 4, 5, 6, 7, 8, so on. Okay, so you have like a 3 for this methyl chloride. Whereas methane, you have like a 0.2. This is 1, right? 0.2 means somewhere here. So just like 0.2. Okay, for methane. So tell me what is this? Why you are getting like a delta value of 3 for methyl chloride, delta value of 0.2 for methane? What's the reason? Yeah, no one understood or what?
Sir, is it because it is shielded with fluoride ion?
Yeah, that is what I want to know from you. Whether you understood or not, tell me. Where is the shielded proton? Okay, whether it is a shielding effect or de-shielding effect, what is it? Methane is shielded proton or less shielded proton?
So less shielded.
Methane.
So shielded.
The other girl is telling less shielded. You are telling shielded. Tell me the correct one. Why it is less shielded or why it is shielded? Tell me the reason.
So because carbon is less electronegative compared to chlorine.
Okay. So as a result, what is happening?
So the electrons won't be pulled from hydrogen. So it is shielded.
Very good. So in methane, all the protons are highly shielded. Yes or no? Each proton, it is having its own electron. The carbon is not electronegative, so it will not pull the electrons towards it. As a result, the electrons will be surrounding like each proton here. Okay, so as a result, the protons are highly shielded. So highly shielded means it will appear either in a downfield or upfield. Come on here. More shielded upfield, less shielded lower field. So this is your upfield, right? So this is your downfield, lower field. Okay, so more shielded, so it will appear 0.2 as a very upfield. Okay, so whereas here you are using 1 chlorine, so you see the difference in delta, right? So huge difference. Only 1 chlorine, huge difference. Okay, because the chlorine is highly electronegative. It will try to pull the electron. As a result, okay, so this is showing comparatively less shielded. This is highly more shielded. This will be less shielded. So less shielded, by default, it will appear low field than the methane. So original methane is appearing here. Methyl chloride will be less shielded towards this. So it is appearing around like delta. CH2Cl2. Again it is like 5.3. So somewhere here. 5.3. Okay. CHCl3 is appearing 6, 7, somewhere here. Right? 7.2. Still lower field. Is it clear?
Yes, sir.
What about the other girl? Somebody told in a reverse.
Yes, sir.
What's your name?
So Sadia.
Okay, so now you are able to understand Sadia.
Yes, sir.
What about other students? Come on, yeah, I'm not hearing from others like Divya, Bharat, Chandini, Nisi, Hema, Satish, Madhangi, Arnav, Vishal. Are you guys here or doing some video game? What Vishal?
No, sir, we are here.
We are here.
You are able to understand, right?
Yes, sir.
Yes, sir.
So the basic thing that you should know, like if you are having like a shielded proton means, okay, so more shielded proton, it will appear in the upfield. Less shielded proton, it will appear in low field or downfield. Okay, that you have to remember. Forget about this value. Okay, so you should think of the scale. Okay, with respect to TMS. Okay, with respect to TMS, your scale you should remember. Okay, so more electronegative atoms de-shield. Okay, the more electronegative atom de-shield more and gives larger shift value. Okay, So effect decreases with the distance, and additional electronegative atoms cause like a increase in chemical shift. Okay, so here you can see like a different types of proton and its respective like delta value. So CH3 alkane, so it will be having like a 0.9. So 0.9 means so somewhere here. Okay, so CH3 like where it will appear here. Okay, and alkane if you see, okay, CH2 CH3 it is 1.3. CH, okay, then it's like 1.4. CH3, well, you have a C double bond O. Okay, so you see the effect. It is like a 2.1. Why it is? Because you have like oxygen here. Okay, adjacent to this carbon, you have like oxygen. So immediately you can see the like delta value highly shifted. Okay, and you can keep on seeing it's like you have like a double bond like carbon and hydrogen. Okay, the chemical value, the chemical shift is like highly shifted. And this is pH hydrogen. What is this? What is this? pH hydrogen. This benzene. Okay. Don't think about why this pH. It's like just phenyl. Okay. C6H5H. Okay. So these proton will be having like a higher delta value. Right? Okay. So you can see here like so aromatic protons. As I told you here, like aromatic. This is like aromatic proton. Benzene. So value delta value will be like around like 7 to 8. Okay. So you have like a benzene ring here, right? You have this proton. Okay. So here, so it will induce the field. Induced field reinforces the external field. So it will be like having like a de-shielding. Okay. So that's why you have like a delta value of like 7 to 8. Okay. And if you see the vinyl protons, okay, again here like induced field reinforces the external field. So that is showing the de-shielding effect. So that's why you have like a delta value of like higher value. So here acetylic proton, okay, in acetylic proton delta value is like a 2.5. So here it is shielding effect. Okay. So shielding effect means you will have less delta value. De-shielding effect means you will have higher delta value. So this you should remember. Okay, don't confuse yourself. Okay, so here you can see like CHO, aldehyde proton. So aldehyde proton, you have like a de-shielding effect. Okay, so as a result, higher delta value. Okay, so you should not confuse yourself. Okay, so I will stop here. Okay, and so I have given like basic information about like NMR. Maybe we'll continue next week. All right. Okay, so do you have like any questions?
Sir, will you conduct second internal?
Yeah, once I finish this unit, I will conduct the second internal.
Okay, sir.
Yeah.
Sir, regarding lab, you said you will be sending notes.
Yeah, I prepared one file. Today I will send you for the first lab session. I will send you. Okay. And
Okay, sir.
just a second.